Yeah. So it's a pleasure to have Adam Levine from IAS, soon to be MIT. So we'll take credit for all the good parts of the talk. To tell us about quantum error correction in SYK and bulk emergence.
Okay. Thanks, Daniel. Thanks for the invite. It's been great. First conference that I've been to since in person since the end of, well, the beginning of COVID, I guess. I wanted to say the end of COVID, but that's definitely not true. So, Oh, you're right. That's my home institution. It doesn't count. Sorry, I didn't mean to forget that. So that was a great conference. Okay, so this is a talk based on this paper that I wrote with Ben. Came out a few months ago. The idea of this talk, well, I feel like the ideas of how the bulk emerges from the boundary have been refined over the years, and originally it sort of started with this idea of RG flow, and that's not totally wrong, but maybe it's not the total story. And then I think important work happened when Daniel and Ahmed and other people started talking about how the bulk emerged through quantum error correction. But there was also sort of this other story happening simultaneously about how when you ping the boundary, the perturbation grows, and somehow the growth of this perturbation is related to the radial direction in the bulk. And I always felt like they should be related, and conceptually they're a little bit similar, but I wanted to make that a little sharper. So that's the goal of this, is to sort of relate these ideas of quantum error correction in ADS CFT to these ideas of what's called operator size growth. And to talk about that relationship, I need to review for you quantum error correction really quickly. I'm sorry for doing this, but I guess I just have to. I'm sure you all know what I'm about to say, but let me just do it quickly. So in quantum error correction, we have some code subspace, right? And there's an isometry U, let's say, which embeds this into some physical Hilbert space. So it's some system that we have in the lab. And there's the logical subspace, which for the purposes of this talk is actually going to be two-dimensional. So our code subspace is going to be super simple. It's just going to be one qubit. It's a qubit's worth of information. But the physical Hilbert space is going to be a system of, let's say, n qubits. So it's going to be 2 to the n dimensional. Okay. So this is sort of a very simple version of a, well, relatively simple version of a quantum error correcting code. And we say that, so the types of codes that I'm going to be considering, holographic codes, have this nice redundancy property such that I have a lot of freedom in choosing which subset of the n spins qubits I pick in order to reconstruct the information. So we say that this qubit is reconstructible on some subset of those n qubits if for any operator acting on the qubit Hilbert, the logical Hilbert space, O code, that if we map that state into the physical Hilbert space, there exists an operator on that subregion, what's called A, which has the same action on the code subspace, right? So this means that A can reconstruct the qubit, logical qubit. Okay, so the picture to have in mind is the standard ADS CFT picture. So we have some boundary region A, and we have some qubit in the bulk, right? And the work of Daniel and co told us that there's a nice geometric way of understanding what you can reconstruct using the RT formula. And so you have some RT, some entanglement wedge, and this qubit that's sitting there can be reconstructed to A, right? So the Hilbert space that I'm often going to be interested in is sort of the Hilbert space of vacuum ADS, let's say, and vacuum ADS with an excitation. maybe this is the excitation there. Okay, so that's my two-dimensional code subspace. So the qubit is telling you whether or not there's a particle sitting somewhere in the bulk. That's the logical qubit, and then you're encoding that information of whether there's a particle there in the boundary. Okay, that's I'm done with the review. So what I wanted to the conceptual idea is that if you have a qubit in the bulk, somehow it has some dual boundary picture, and it could be represented as some size, right? As some operator with some size. And as you put the particle deeper in the bulk, conceptually the size should grow. And I want to relate that to an idea of how hard it is to reconstruct this operator, not in the sense of complexity, that's a much harder thing to compute, but in a different way, which I'll now describe. So there was this really nice paper when I was a grad student by Pistowski and Preskill. Where they introduced these two concepts called the price and the distance. For this talk, I'm going to mostly be interested in the price. So the price of a quantum error correcting code, P of H code. So it's a function of the unitary or that embeds the Hilbert space into your physical Hilbert space. It's the min over all subsystems of your physical system of the size of that system. I'll come back to that in a second, times such that H code is reconstructible on A. Okay, so it's sort of in this talk and in general, we could argue about what I mean by this here. It's some measure on the subsets of your system. For this talk, since I'm talking about qubits, the canonical obvious measure is just take the number of qubits in your subsystem, right? So how many physical qubits do you need to reconstruct your logical qubit? That's the price, okay? It's the price of, it's the cost of trying to reconstruct that. They also introduced this quantity called the distance, which is a sort of dual quantity, which is the min. So the distance, I won't need this, but let me just say it, is the min over all boundary regions, size of the boundary region, such that erasure of A is not correctable. So meaning if you lose A, you lose the logical qubit, at least partly. You lose some information about the logical qubit. So here's the picture to have in mind. You have ADS, so you have a bunch of matter in the bulk, let's say, maybe a bunch of qubits that are sitting somewhere in the middle. So the price is the size of the minimal boundary region such that you can reconstruct all of these qubits, right? And the distance is the size of the minimal boundary region such that if you lose it, you can still reconstruct it on the complement. Okay, so this is the distance, and this is well, the distance, the size of the, sorry, I shouldn't have done this. Sorry, there you go. This is the distance here, and this is the price, would be the larger region, right? It's price, distance. Okay, so it's clear from this discussion that the price is generally bigger than the distance. If this were a really small, if you localize this this code subspace, say to one qubit that's localized at a point, then in ADS CFT, you get this special thing that the price and distance are the same. Yeah, do you want a question? If the Ryu-Takanagi surface is at a phase transition?
Something that is, so there's a region for which
I think in that case, it's a bit subtle about what you can actually, when you're right at a phase transition, it's a bit subtle about what, I think the smaller one is really the one that you can reconstruct, the smaller code subs, the smaller entanglement wedge.
But then you go epsilon away from that and you can already reconstruct something bigger. So then the.
Yeah. Yeah, I think the price and distance are equal if the code subspace is associated to something, information that's localized in the bulk, right? So that would be I think in that case, yeah, I'm not sure. Yeah.
In your example, the two minimizing regions are nested on the boundary.
Yeah, I don't think that needs to happen. I
That's-
just drew that.
That's
that way.
not.
Yeah, yeah. Okay, so so the goal of this talk is to try and associate a price to an operator. So far I've told you how to associate a price to a code subspace, but how do I associate a price to an operator? So imagine that we have some preferred state, which I'm going to suggestively call beta, which will be the thermal field double. And you have some operator acting on the physical Hilbert space, phys. And for simplicity, I'm going to assume that the 1-point function of O in this state is 0, but if it's not, you can modify things a little bit and it still works, but let's just do that. So I'm going to call the 0 state of my code subspace. I mentioned the code subspace is 2-dimensional, so the 0 state is just the thermal field double, and the 1 state is O acting on the thermal field double. Okay, so I insert some operator, let's say at some time on the boundary. In general, this will be the position of this operator will be time dependent, and I'm going to insert it, let's say, on the right. And then the code subspace is just O code of O and beta. It depends on this operator, and beta is just the span of these two states, okay? And then I just associate the price of an operator, which depends on this reference state beta, as P of this code.
So
Okay.
Adam, just to be clear, you're not or don't have to assume anything about how O acts on O beta.
Other than this fact that its 1-point function is 0, so the two states are orthogonal.
No, yeah, no, I know, but I mean, if I act with O on the state O beta, then
Yeah.
that gives me something involving a product of.
Yes, good.
I think.
So
you're not assuming
I
anything
think
about that.
right. There's this temptation, right? So what are the logical operators?
Yeah, it's not
The
clear.
logical operators
operator,
don't
though.
have a nice. These are not operators that we're used to dealing with in
Yes.
CFT, for example.
Uh-huh.
These are operators that really act on the full CFT Hilbert space, and then we're going to try and reconstruct them on some subspace.
But just acting on beta, not acting on O beta.
Yeah. So the operators. So let me just write this. So my poly operators are going to be like beta O plus Hermitian conjugate. Let's say that's sigma X and then sigma
Yeah.
Y.
Okay. So that's what you're actually going to try to reconstruct. You're
Yes.
not going to try to
Yeah.
reconstruct O.
Right, that's right. Reconstructing the O and its action on the whole Hilbert space would be quite challenging. Yeah. And that would correspond to a code subspace of very high dimension. Yeah. Okay, so let me just so I have these two poly operators. Okay. And then you get sigma Z this way. Okay. So this is our definition of the price, and the basic the goal of this talk is to compute this thing in SYK and write a formula for it in terms of the size of the operator. So O has some size, and there's a relationship between the price of the operator and the size, which I'll prove. And okay. So are there any questions? Let me tell you now how I compute the price. Okay, so as I said earlier, I'm going to take beta to be the thermal field double. So it's on two systems, L and R. So here's the thermal field double. We have left system L, right system R, and they're entangled in some way, thermally entangled. And I'm going to pick some subset of the right, which I'm going to call little r. And then for reasons that have, just stuck, I'm going to call the rest of this K. So little r is big R minus K. And the complement of little r is L union K. Okay, so LK is R. And the question is, when can we reconstruct the action of sigma X and sigma Y on little r? When is that possible? When it is possible, or just when it's on the edge of being possible, then if I have, let's say, n qubits here and n qubits here, then the price of the operator, the minimum overall r, such that it's still reconstructible, the price of that operator will be n minus k, right? So I'm going to dial k until, let's say, until I can just reconstruct it, just barely reconstruct it, and then that will be the price. Okay, so how do I find this special k? That's the question. So what we're going to use to do this is the relative entropy. So as Monica said yesterday, as we all learned in high school, the relative entropy is a is a function of two density matrices, and it's a distinguishing. It distinguishes basically. It tells you how distinguishable the two states are. So when it's very large, the two states are, roughly speaking, in some sense, distinguishable, and when it's small, they're not. This is not rigorous, so the relative entropy is actually kind of a tough thing to deal with because it's not continuous. So take everything I said there with a grain of salt, but there's a better way of doing this that doesn't use the relative entropy, but for the purpose of this talk, I'm going to use the relative entropy.
I mean, I'd say there is actually a rigorous sense in which it's measuring the distinguishability of states, right? And Renato can probably.
So all I meant by that was that Pinsker's inequality only goes one way. And the relative entropy can be huge despite the fact that operationally the two states are not the same.
There's a particular task for which, there's a particular distinguishing task for which that's the right.
Sure, fine, that's fine. I just mean for the purposes of reconstruction, it's not actually the relevant quantity.
Yeah.
But for this talk, it'll be good enough. Okay. Okay, let me actually, so let me go.
Something basic. O is just on the left, or I mean, just on the right, or?
Yeah. So the operator I'm going to try and compute the price for is going to be an operator inserted on the right. So I'm going to insert. So my code subspace is going to be OR acting on beta and beta. Those are my two logical. And I'm going to time evolve R with respect to the right Hamiltonian so that I can insert it, farther and farther in the past or in the future and ask about how its price changes. Okay, I mean, this is basically this is literally Hayden Preskill. All I'm doing is computing some things explicitly and finding some relationships between ideas that had already existed. So if you know about Hayden Preskill, then just think that. Okay, so how yeah.
Basically a particle that either close the boundary or close the
Yeah.
horizon and right from the opposite.
And we're trying to reconstruct it. Yeah.
That's always outside the horizon, or else.
Yes, it's always outside the horizon. Yeah. Yep. Okay, so how do I compute the price? I said I was going to use the relative entropy. So what I'm going to want to do is, well, what will be useful is consider the state e to the I lambda sigma x acting on beta. Okay, this is some unitary which acts on beta, and I want to know if the relative entropy between e to the I lambda x, lambda sigma x, and beta reduced to the R region is bigger than the relative entropy between the two states associated to its complement. Okay, so again, heuristically, when this quantity here is large and positive, then it's reconstructible on little r. When it's large and negative, it's reconstructible on LK. The reason is that the states on little r, when this is large and positive, are more distinguishable. And again, and on the right. When this is larger, it's more distinguishable. Okay, does that make sense to people? That's the reason this is a nice quantity is because this is actually just equal to sine squared of lambda times sigma x log of delta r sigma x, where delta r is this generalized boost generator. So you take the density matrix associated to the thermofield double. So this thing sort of generates sort of generalized boosts in some sense, right? So it's just an expectation value of this boost operator in the, it's sort of a generalized boost energy in the sigma x state. But sigma x is acting on this is in the thermofield double, so this is just sine squared lambda O, let's say, of TR R log of delta R in the beta state. So this is some correlation function which we can try and go and compute. It's related to some modular flowed correlation function, but basically it's just a correlation function. Okay, so we want to find the K. So what we do is we compute this for general K and then dial K such that this thing is 0. Okay, so we're going to define, if this is delta S of K, we want to find the K such that this is 0, right? That's roughly speaking right when it's on the edge of reconstructibility, okay? Or really you want to find the smallest or the largest, the largest K such that this holds. In systems like SYK, there's an ON, I mean, I can permute all the spins and so there's no preferred choice of the K. So it really just is dependent on the total number of K. But in a more complicated system, you might have to, use the details of the theory to actually find a specific K that actually works. And it's a very complicated thing. SYK is simple enough that we can do the calculation. Yeah. Oh, sorry. Oh, I thought you said something. Okay. Oh.
I would have thought that when you're analyzing who can reconstruct what,
Yeah.
you might have just say looked at just the relative entropy in the complement LK and seen that it's small or something, and then concluded that you could reconstruct it on little r. But it seems like, so here you're doing something more sophisticated, a difference in relative entropy.
A difference in relative entropy. Yeah, in some sense it's less sophisticated because it's easier to compute than just the relative entropy, which is partly why I'm computing it. But yes, I mean, what you see in these systems is that when this guy dips and gets small, the other guy comes up at basically exactly the same time.
So this is easier to compute. It has the same.
This is easier to compute and has the same information.
Okay.
Yeah. Okay, and as I said, then the price of that operator is n minus k star, right? Okay, so that's what we're going to do. This is what we're going to end up doing in SYK. But before I get to SYK, I wanted to prove a relationship between the price and the size. So to relate this to the size discussion, I need to introduce size, which I think someone did, but let me. Okay, so operator size. A lot of people have talked about this, but where I learned most of what I'm going to be telling you is from this paper by Stryker and Chi. Okay, so let's imagine you have some system of n spins, right? Then you can write down operators which are words of polys, maybe like this, acting on each site, blah, blah, blah. And the size of this operator here, which I'm going to denote by this, is going to be the number of sites which are not equal to the identity operator. Okay? So it's a very simple definition. And these strings of polys like this form a complete basis for your operators. So any operator O on the system can be written in some basis Cp of P, okay, where you sum over all such poly operators. And there's a natural state to consider, which is this maximally entangled state, 0 on, so you have 2 copies of your system, and you look at all the state where there are all Bell pairs between the 2 systems. And then there's a basis for this tensor product, which is what we'll call the size basis. So it's states with definite numbers of operators acting. And the reason this is nice is you can think of this sort of as the infinite temperature thermofield double, right? So to get to the thermofield double from this guy, you just act with some Euclidean evolution, and you can get down to finite temperature, okay? And there's an operator, there's not a single-sided operator that will measure the number of polys, the number of sites that are activated that have some poly acting on them. But there is a 2-sided operator, so this is called the size operator. And we're going to denote it by Vn, and it has the following form: 1 over n, sum over all the sites of 1 minus sum over all polys on that site, pi, p left I, p right I star. Okay, I'm not going to prove that this acts the way it does, but it's not hard to show using, undergrad QM stuff, that this acts in this way. So these p operators are eigenstates of this Vn with eigenvalue given by the fraction of sites that's activated. Okay. Something that will be important for us. So this is the size. This is the total size of P. But you could do something which is called the K size, which will be very important for this talk, which is where you just restrict this sum to be only over a number of sites, some preferred subset of sites, okay? Which is the same thing, okay, as above. And this acts, so Vk on P acts as Pk divided by K. So it's the number of sites within that case, that K subset that have polys acting on them, okay? And well, something that will be important for the talk is that V, for a sufficiently scrambled state, so if we have an operator that's sufficiently scrambled in some sense, maybe you evolve it back in time for long enough, that Vn is approximately Vk acting on that state. The reason this is true, right, is because these are fractional sizes. So basically, if you imagine that the operator is scrambled enough, then if you take some subset K of the spins and you act about the size on that subset, it'll be representative of the total population, right? So that's why these operators basically act the same. Okay, so as an aside, SYK in terms of fermions, so SYK, the fundamental degrees of freedom, are these fermions, and you can write the operators in terms of some basis of fermion operators, and then Vn has a nice formula in terms of summing over fermion operators. I equals 1 to n, 1 plus I psi left, psi right. Okay. So just to say that later when we come to SYK, that's what I'll be using. But okay.
That's the equation. Not only you have this, but also approximately 1.
Yes. It's 1 minus, I'm going to be working in a regime where it's 1 minus a small amount, and the small amount will be important. But the time at which these become approximately equal is before it reaches really n size. Yeah, you just need that it's sufficiently Okay, and now the final thing that I need to introduce, which is not my own work so far, none of this has been my work, I'll get to it soon, is size winding, which thankfully we have an expert in the audience, so if there are any questions on it, I'm just gonna relay to Henry. I told you shouldn't come to my talk. So size winding. So there are these nice set of papers. They have a bunch of authors, so I'm just going to go by the name. It's QG in the lab. Probably everyone knows about these. Where they look at operators in theories that exhibit maximal chaos, and they find that if you expand, let's say, a simple operator that's being time evolved in this size basis, so you have some operator O of t, then this operator has some expansion, as I said before, in terms of these polys. These size wave functions have a very nice form, which is that they're just basically a real phase, a real part times a pure phase, where this phase depends not on the specific detail of which p you have, there are many p of the same size, but just on its size. And this alpha here is some constant, okay? So this is a very special behavior, and so RP is just some real number. Why is this interesting? Why do we care about this? Well, I'll explain in a second that when this happens, you can do a teleportation protocol. But okay, so in what we're considering, right, OR of TR, we want to compute its size. Actually, it'll be simpler for us because of this rho acting on the maximally entangled state. It'll be simpler for us to compute the size of this guy and subtract off the thermal contribution. But just think of this as a thermally subtracted size. And in terms of these guys, this will just be sum of RP squared P, right? Basically. Okay, but what is this alpha here? And now I'm going to prove for you a bound on the price in terms of the size by computing this alpha for you. So this alpha here has a known form that you can write down. In these, so what is alpha? So a stupid thing you can do is just differentiate. So let's say you have an operator which you insert at some on the right with some time tr. So you can differentiate this thing with respect to the time, and just using Schrodinger's equation, this will be delta H. You can write this as delta H times O right beta, where delta H is this full Hamiltonian, it's H left, H right minus H left, right? But if I use the fact that this thing is size wanding, so I put in this ansatz for the size coefficients, I can write this as sum over all polys alpha dot, because that's the only thing that depends on time. Sorry, that's not the only thing that depends on time. There's one other thing. Right, so I have these e to the I alpha p's here up front, plus a term which goes like rp dot p e to the I alpha p. Okay? But now if I take the expectation, so if I look at the expectation value of the energy in this state, so OR delta H OR beta, so this is the boost energy of the particle. What I see is that actually this term vanishes because, well, you'll end up just getting the derivative of the norm of the state, and that's 0. So all we're left with is alpha dot. You can see all we're left with is alpha dot times the size. The phases will cancel, and we just get the size. So this tells us that the derivative, the time derivative of alpha dot is just the energy of the state divided by its size. So it's the energy of the operator divided by its size. But in this regime, when you have size winding, the size generally is growing exponentially with time, like 2 pi t over beta. And so you can integrate this equation and you just get alpha is basically the energy times beta over 2 pi times the size. Okay, so that's this equation. So it's just writable. This alpha is writable in terms of the size. Okay, and now knowing that, well, then I can figure out how to teleport this operator pretty easily. Okay, so I think Vincent was talking about this. There's this teleportation by size protocol, although he was at very late times. So let me do reconstruction by teleportation. So the idea here is that I have the thermal field double, and I insert some operator O right at some time in the past, let's say, and it falls in. And I want to get it out to the left. I want to represent it as an operator O left of T right. Well, if you assume that O right is size winding, right? So its action on the thermal field double has this nice expansion, RP e to the I alpha p. Well, it's a fact that O left at minus T right on the left, the minus here, right, is just because time evolution goes in the opposite direction on the left versus the right, is actually just the same thing, but where I flip, you can convince yourself that all I do is I flip the phase here. So if I could act with some operator on this state that effectively just flips this phase, then I've teleported the operator. That's the statement. And well, we know an operator that acts simply in the size basis. It's these V operators that I wrote earlier. So actually, what we need to do is act with an operator e to the IGVN, let's say. Or in our case, we want to do it by only restricting to a subset K. If we can tune G, we can then tune G such that it's dependent on alpha. So we can get a formula like this. If G obeys the equation, G is minus 2n alpha. Okay? So we need to be able to tune this coefficient such that I get this. But the overall coefficient here is not that important. It's just it's scaling. So it's n times alpha, but alpha we said is the energy of the operator divided by its size. Sorry, this was for Vn, excuse me. But if we only had access to k qubits, let's say, on the right, and not all the qubits on the right, so this is possible if you had access to all the qubits, both on the right and the left, because this Vn here is supported on all the qubits. But let's say we did a different protocol where we just wanted to do teleportation, but using only k qubits on the right. Then you would need to do this just with this VK operator. Okay, so what will happen is that you'll end up getting that G needs to be enhanced relative to the previous G. Let me see here. Actually, let me do something else first. Okay. But this, okay, so I set up here reconstruction by teleportation. This is not actually reconstruction when you act with this guy. The reason is the operator, I haven't actually found an operator on the left which acts as the operator on the right. Well, in particular, I haven't found a Hermitian operator on the left that acts as the operator on the right. So what I really want to do is act with e to the IGVN, let's say O left, with the minus e to the IGVN. This operator, according to that formula, would act the same as the guy on the right, and it would be Hermitian, right? But to do that, I need that this state is an okay thing, or it doesn't do much to the state. So what I need is three conditions. So if I wanted to reconstruct this operator, the right operator on the left, what I need is that VK OR of TR. I need that the operator is sufficiently scrambled. Furthermore, I need that e to the IGVN, or VK, acting on beta, is approximately e to the IG VK, meaning it acts as just a phase. So what's special about this operator, so if this guy just changes the state by a phase, then we win, because we don't care, well, the phase doesn't actually matter in the end. And what I need also to reconstruct using V is that G times K over N is twice alpha, right? So here, basically, it's this formula, except now I have an extra factor of K. So because PK over K is P over N, I get that PK is P times K over N, right? So I need that the size, the K size, I get this extra factor of K over N here, right? Yeah, okay. Good, okay. Are there any questions about this? Sorry? Here? I want an N. Let's see. Do I want an N? When K is equal to, I think I messed up a normalization here. I think that's what's throwing me off. Sorry. Let's see here. Did I mess up a normalization? Yeah, for some reason I'm in trouble. Hang on. I think I just need that. Why am I having so much trouble with this? BK. I think you're right, but why are you right? Yeah, I think you're right. I think you're right. Sorry. So we need that G is VK. Sorry, G is K. 2 alpha over K, I think, right?
Sorry, Adam, can I ask you a question?
Yeah.
Why are you calling this reconstruction? Can you explain why
Oh, sorry.
operator reconstruction?
Why is it reconstruction? Because I found an operator, a Hermitian operator on the left, which is equal on the code subspace.
Sorry, it's on the left?
Sorry, maybe this wasn't clear. I'm trying to reconstruct by teleportation, right? So I'm trying to act, I have an operator which I've acted on the right. I'm trying to reconstruct it on L union K.
I feel like it would be more natural to think of this as state-specific reconstruction beta. I think if we call it that, maybe, right? Because you're just trying to act on beta, right?
Yes, it's state-specific, yeah.
You're reconstructing
that's right,
O
that's right.
on beta.
That's right.
And
that's right.
does anything break if you take O to be a unitary? I'm just curious, or we could, I guess.
If I take O to be a unitary?
Yeah, then it's
No.
will the reconstruction be unitary? I mean, that's the only other thing we might ask for.
No, well, sorry, that's the key point. That's why I said if you start with a Hermitian operator, you want the final thing to be Hermitian. Or alternatively, if you start with a unitary operator, you want the final thing to be unitary.
Yeah, somehow it's a little bit harder to be unitary than it is to be Hermitian. I mean, somehow like Chris and Jeff they couldn't just require that the reconstruction of a Hermitian operator is Hermitian. They had to require that for a unitary operator, the reconstruction is.
But if you have,
No, you don't get to exponentiate, that's the thing, because you're only acting on one state.
no, but if you have a Hermitian operator, well, okay, maybe just to satisfy you, I'll just say that if you have a unitary operator, nothing breaks.
I think it should be unitary, I'm not saying it's not.
Yeah,
I was just confirming.
Yeah. Okay, but this condition that it's a pure phase, which is key for preserving unitarity, is only true for large n systems if G is sufficiently small. This comes from, well, yeah. This basically, the way to think about this condition is that if G is too large, I'm really doing something, I'm turning on a source on the state, and it's really throwing in a bunch of energy, and it can back react in the bulk. So you don't want G to be too big, and the condition such that that doesn't happen is just that G is sufficiently small. It's order 1. It doesn't scale with any of the large parameters here. Okay. Good. So, right. So, but what that means, right, if I use this formula here, is that if I use this bound, I get that K needs to be less than or approximately equal to 2 times alpha, right? But alpha, we said, sorry. I'm getting this confused. G needs to be less than or equal to approximately n for this to work out. Sorry. That's better. Yeah, that's what I meant. Yeah. Sorry. This fixes my. I think it's n. The reason is that this k comes with a 1 over, this vk has a 1 over k in its normalization.
Yeah, no, I'm just wondering whether it should be n or k. Is
N.
K further n or?
K is much less than n, we're assuming here. So what I'm assuming, so if Vn, sorry, let me write this. I need that this is true, and then G is less than or equal to, and then I'm using the fact that Vk and Vn act approximately the same on the state to say that, yeah. So if G is less than or equal to order n, yeah, sorry, I think this fixes my normalization confusion that I had. Sorry, so, okay, good. So now what we get is that G is less than or equal to n times k. Sorry, I don't know what happened to me. It should really be k over n. I think actually this is 1 over n. Sorry. Oh, God. Yeah, anyway, there's some scaling here, which is 2 alpha n, and alpha n is approximately n times the energy over the size. Okay, so in order to do, the basic idea is that you need at least enough qubits such that you don't need to perturb the state too much, okay? And if you don't need to perturb the state too much, and you can still reconstruct, right? That's where the bound comes from, is basically this fact that you don't want to disturb the state. And given that alpha has this scaling with the energy over the size, you get help from the fact that the operator is growing in size. Okay,
but just very naively, okay?
Yeah.
I would have thought that making big N bigger makes it harder to disturb the state. But that's not what that inequality looks like.
It has to do with the V scaling, I'm sorry. Yeah,
okay.
I can't, it has to do with the way I normalize V.
Yeah. Okay, well, yeah, we don't have to sort it out in real time.
Sorry, yeah, I should have sorted this out earlier. Yeah, I think I missed a 1 over n here. I think there was a response to Henry and that this is over 1. Yeah. But anyway, okay.
Yeah.
Yeah. There was some mistake I made, but can't figure it out right now. Okay. All right, so why did I take this huge tangent? The point is that to compute the price, you need to know that the operator can't possibly be reconstructed on the complement, because if it were reconstructible on the complement, then by no cloning, you can't reconstruct it on your system. So what that means is that given that for k bigger than this amount, right, bigger than this amount, I can reconstruct by teleportation. The price of the operator needs to be, price of O needs to be n minus k star, which is n times 1 minus e over the size, where there's some numbers here. Okay? So roughly speaking, this is telling us that quantum teleportation, that you need a minimum, you need to share a minimum number of qubits between the two sides to accomplish quantum teleportation. Okay, how much time? Not very much. So let me just briefly go into SYK. So SYK is a sum of a bunch of spins. The SYK Hamiltonian is a bunch of terms like this. So I have Q fermions, let's say, and random couplings. We all know about this. So as I said earlier, I want to compute, so my operator O, in this case, is going to be very explicitly this e to the IHT, psi, e to the minus IHT, okay? And I want to compute, I told you earlier, I want to compute log of delta R, OR, right? The expectation, this generalized boost energy, and look when this generalized boost, this difference in relative entropies, so this is this delta S of K, when does this become negative or 0? When does it cross between being positive and negative? So how do we compute this? This is just a difference in modular energies, which you can compute via a replica trick. So the replica trick looks something like this. The replica trick is the following. So we prepare the thermal field double, and I'm going to draw two lines here. The line here, so this side of a thermal field double is R, and this side of a thermal field double is L, and I have two lines. I have little r here and big K. Okay? So this is the, and this picture makes it look like they're decoupled, but actually, you know, this Hamiltonian mixes them up, so really I should think of these two lines as sort of exchanging particles. And then what I'm doing is I'm computing a state where I insert some operator psi on the right, another operator psi on the psi dagger in the ket. And then I want to insert twist operators. So basically this replica trick here involves inserting twist operators on the regions that you're interested in. So we have sigma minus n on K and sigma n on L, okay? And it turns out that there's a nice formula for these twist operators. Well, you can expand any operator in a complete basis of states. So you have some expansion like this, I equals 1 up to K. Right, so this operator is purely supported on the K subset, so I need to only expand it in terms of a set of operators, Cij, psi I, psi j, where this sum here runs from I equals 1, j equals 1 up to K, and so on and so forth, and there will be higher fermion number operators, but we can expand in some basis like this. And it turns out, Ben and I did the calculation, you can actually compute these guys at large beta j, so at leading order at large n, small k over n, so we took this limit, and then also large beta j. And it turns out that in these limits, these higher fermion number terms just drop out. They're not important, and you just get a simple formula in terms of a 2 fermion operator with some coefficients that are computable. And what the final answer is, when all is said and done, is you get an explicit expression like log of rho Lk is log of rho L plus a bilocal term that looks schematically like this. There will be other terms here, which again are higher fermion numbers, but the leading 2 fermion operator term just looks like a bilocal coupling between the left and the right. So this operator is very reminiscent of the size operator, which I said was a sum of bilocal operators. And so what you find in the end is that the expectation value of this guy, you get a formula, which is that psi log delta LK psi is equal to the log psi log delta L plus effectively this size operator here. So I'm going to think of this as the size operator up to order 1 coefficients. And what you get is minus k times size over n. And this is the boost energy. This is also called the boost energy. So this is 0 when k is equal to energy times n over the size. And again, there are some order 1 coefficients here. But the point is that parametrically, quantum teleportation by reconstruction by quantum teleportation actually does as good a job as you can possibly do. It's the most efficient protocol in this small k over n limit. So this is the k. This told you what is the most efficient thing that you could possibly get, and it matches parametrically with this answer here. Let me just comment in the end, just one last thing, that because this size operator is showing up, what you end up getting is a nice formula for this operator. So there's a QES in the bulk. There's a way of interpreting this as a QES, which is that delta LK to the IS, delta L to the minus IS, is e to the IP, e to the 2 pi s minus 1, delta L, delta XQ. So actually, when all is said and done, you can compute this guy, and using this formula, you find a half-sided modular inclusion algebra, which was recently discussed by Liu and Leuthauser. So this tells us that this algebra of spins, L union K or little r, and the large N limit needs to be type 3, which, okay, maybe not totally surprising, but it's a nice thing to see explicitly in SYK. And furthermore, you can compute this quantity here. So this looks like what this is doing is it's generating a null shift for you. And the statement that we argued for in the paper is that there's actually a QES in the bulk associated to the subset little r, which sits somewhere an amount delta XQ plus away from the bifurcation surface. And you can actually explicitly compute this in terms of SYK quantities, and it's equal to k over n beta times delta over 2 pi phi r, where phi r is related to the Schwarzian coupling in SYK, and delta is just the dimension of the boundary fermion. It's 1 over q. And this answer matches exactly with, sorry, there's also a 1 over beta j to the 2 delta suppression here. This answer matches exactly with a bulk picture where you have n free fermions. Well, it doesn't match exactly, but it matches qualitatively with a bulk picture where you have n free fermions, and you have a QES somewhere out in the right exterior, and it's associated to some near boundary region, which is order beta j away from this bulk region. So this is kind of a surprising thing to me, at least. I mean, from one angle, it's not surprising that quantum teleportation and reconstruction are related, but it's also surprising that you get sort of a picture that seems to work very well for a QES associated to a subset of spins in the boundary. Like, there's no spatial structure. We're used to this. I mean, I guess we expect this to happen for the radiation in a black hole, but still it was sort of fairly explicit here and in a surprising way, I guess. Okay, that's all I have to say.
All right, thanks, Adam. Tom has a question.
Yeah, so the shift that you just drew is not obviously associated to a half-sided modular inclusion. So How are you?
Yeah, you're saying, yeah, right.
It's space-like.
What I mean is that for operators far in the past, it approximately acts that way.
Okay, so you have to make that qualification, or is there some operational thing you
Yeah,
can do to actually give you the?
yeah, it's a good question. There's probably a way of extracting just purely the P from that operator, but I agree. I mean, one way of saying it is what you kind of want to do is take K and boost K up, right? But I think that amounts to just considering only operators that are far in the past.
So you kind of want to do that in some independent way or some.
Ah,
'Cause you
maybe.
have to take a limit at some point.
maybe, yeah. That's a good idea.
Does this suggest anything about how we're supposed to think about, you know, the flat space limit of holography, or if I only have a subset of the matrix, the degrees of freedom?
Yeah, I mean, right, you could do a similar thing in, say, this ungauged BFSS model, I guess, right, where you consider a subset of the matrices. I don't know. This story really depended on this chaos business, and if you don't have control over that, or you don't know if it's there, I'm not sure how much of the story will port over, but yeah, it's an interesting.
Even if there's just a plausible story you can tell rather than a set of calculations that would already be useful.
I mean, for me it opens up other questions about what are the algebras. I mean, I guess this is what Liu and Leuthauser discussed, but what other algebras can we consider in the boundary, and do they have geometric interpretations?
So you have this entanglement wedge for K spins,
Yeah,
and it's the same entanglement wedge in the Penrose diagram for any K spins.
yeah, it's strange, yeah.
So yeah, it seems like the disjoint systems have the same. Does it come with some index so that there's some sense in which disjoint sets of spins don't have the exact same entanglement
Well,
wedge?
sorry, so it doesn't have, sorry. Oh, you're talking about the near boundary guy?
Yeah, the near boundary guy.
Yeah, yes, so good, right. So what happens is that in the bulk, you have n fermions. Well, the picture is in the bulk, you have n fermions. And as you said, there's an index on the, effectively, there's an index on the entanglement wedge that says that that guy's entanglement wedge can only reconstruct that guy's flavors.
I see, okay,
basically.
okay, I see. So, yeah, okay.
That's the picture. It's,
Sorry, let me see, maybe I didn't understand this
Yeah.
question and answer correctly. So the fermions, the K fermions that you pick
Yes.
could be any of the K fermions.
yep.
And once you pick them, you can reconstruct any of the other fermions, any of the n fermions that is in that entanglement wedge.
If you're given those K fermions together with, let's say, L.
Yes.
But Chris was asking about, there's some sense, when I did this calculation in the, we did a bulk calculation that, that computed the position of the QES, but that bulk calculation inputted that there's a very near boundary region. And we wanted to have that very small near boundary region associated with the K. It's sort of like, it's like in higher dimensional. And Chris was confused about the fact that it seems like these guys are overlapping. But the point is that, yeah, I think the point is that they can only reconstruct their own, like formally the theories are decoupled in the bulk. It's just n free fields, which of course at higher orders and everything, we expect that picture to break. So maybe this picture also breaks, but at least to leading order.
Yeah. Anyone else? All right, let's thank Adam again. Have lunch.
What did I get wrong here? I can't figure out this error that I made.
I think to address Daniel's question, you could have taken your code subspace to be psi I and psi j. Is that possible?
You mean take psi I on the thermofield double and psi j? Yeah. I mean, all we needed to all I needed to claim that I could reconstruct this code subspace was that I could get states like this, right? Sorry, this, beta, and this, right? If I can get all of these guys, then I have the, if I find unitaries on the subsystem that act like all of these guys, then I'm done, right?
I thought Yeah, his complaint was roughly speaking that one inserted matter and the other one did nothing, right?
Right.
But in the case where you just take the index to be different.
Oh, you're saying in SYK because like they're simple.
Yeah.
You're saying like psi squared is 1, so it doesn't generate a huge.
No, all I'm saying is in a code subspace you take this
Yes.
and psi j. Right? Instead of taking beta and psi I, you took beta and psi I acting on beta. Right?
Yes.
But
Right.
you could have probably also just taken
Yes.
this where I
Yes.
did.
Yes. Sorry.
That's
Yes.
fine.
Yes. Yes.
Yeah.
Yeah. To leading order. Yeah. I mean, this guy also, in principle, has a 1-point function. I think, right?
Yeah, this is a bit like just having a shockwave with a qubit on the shockwave.
Yes. Whereas versus yes, that's right.
It's something.
Yeah. I think the answers will all be the same. They might be a bit more. This will be more complicated because what you'll end up with in the end is having to compute things like 4-point functions where the two operators that we normally set to have the same index will have different index. So maybe that's more complicated. Like you'll need to know about off-diagonal correlation functions in SYK, I think, to compute this type of, right? Because,
Shouldn't it be good if there's no off-diagonal correlations? Like, whenever we talk about.
maybe you're right. Sorry, yeah, I think maybe you're right.
Yeah, I'm not sure how it.
What did I do? Yeah, okay, whatever. Can't figure out what my scaling problem was. So these guys act as P over N, whatever. G P over N, and you have alpha P. So you need that G is of order, right?
Sure, it works, right?
And these are, yeah, I'm just trying to remember what I did wrong. This is G P N over K. Yeah, that's right. No, wait, no, it's not.
Just say, look at the picture.
Why is this not working? Okay, anyway, it works in the paper, for sure.
I mean, the final, there's no other way the final answer could depend on k over
Yeah.
It couldn't be k over n is 1 over n squared or something.
Right. Yeah, Tom, your question is a good one though, right, I guess. That this doesn't,
Oh, yeah, so
technically there's other terms here, there's another term.
yeah.
And we're neglecting that other term because we're considering correlation functions that are highly boosted. But
I think
in principle,
Yeah, I think what that means is you actually have to do something funny with your flow with n, right? So S has to be n. And then that will limit to some flow. Yeah, I mean,
sorry, you mean like, I thought, so one idea was just to boost K way up.
isn't that the same?
It's the same, yeah. Sorry, you're saying, because you're saying this is like, the other term is like P, so this is P plus, and the other term is like P minus e to the minus, like something like this. So you can suppress it by taking S of order log n. It is true that we don't get an operator which exactly implements the algebra, but I feel like it should be enough to claim that it's type 3, just that.
Yeah, well, that's a different question. Right? So
Yeah. But this is an interesting thing where you can explicitly see, I mean, the type 3, the fact that it's, well,
that's a good question. It's saturated chaos.
type 3. That's what I would have said. But I don't know. Well, I think the claim is just given maximal chaos, there's some operator which you can construct which obeys the right algebra.
Yeah, well, that's the idea. So I'm still, do you have that idea of, I guess, what this, so I guess usually, yeah, I guess in the half-cycle modular inclusion story, you get this kind of thing out of it. And then, so I guess, yeah, so in this situation, your sub-algebra is this L, and then, so then, yeah, if you have some picture of what the sort of family of shifted L, what the family of these shifted L algebras would be?
Shifted L, so here, yeah,
Yeah,
I can change K and change the size of it.
right.
So I think that's, you have to do both of that, right? So you need to make your proposal is in terms of just SYK. I think that's like, okay, SYK with some number of fermions
Yeah,
kicked out, and then you just take some large n limit there.
yeah,
And then,
yeah, yeah.
but
But the algebra, right,
it
so
seems
in
to be,
that,
and it's
in
just
that
the
limit,
algebra of those
it'll just be type
subsets.
3.
Yeah.
It's the algebra of
But
those.
I guess it doesn't even matter if you take a subset, right? You also expect that to be type 3.
You mean if I take all?
Oh, yeah,
Yeah.
in the
Yeah,
subset,
it'll
yeah.
also- it'll also be type 3.
Yeah.
I mean, doesn't this tell you that all of them are,
I guess
everything
this
involved
is-
in this is type 3?
Yeah,
Is that
okay.
right?
I guess this is like a proof strategy.
Yeah.
Because we expect that there's no proof, but this is a proof strategy. Okay.
It sounds like you're, yeah, sort of bridging, yeah, what Sam discusses with this SL2 symmetry generator stuff.
Yeah.
Yeah. So these are the same as your generators, right? So this is the same thing, right?
Yeah, but I thought they were different. Well, I thought our constructions were superficially quite different. For example, to make our generators, we need the Hamiltonian to be. We need the Hamiltonian.
is superficially different. What,
The Hamiltonian doesn't exist.
I mean,
in
the
Sam.
accident, or it's not, maybe not an accident, the key fact is just that your operators basically show up.
So yeah. Why do you need the Hamilton? You need the left-right Hamiltonian, right?
The left and right Hamiltonian.
Left minus right. Do you need more than that?
He had, oh yeah, you guys have H left.
Yeah, we have H left plus H right plus size, but maybe that also, it could be possible that there's
I
other
see.
combinations are
That's-
special. And
That's the global, that's the global time.
Yeah.
I thought just P is like psi left, psi right, basically. Right?
Well, it sounds like you could take the boost and then your generator and get the third one, for example.
Yes, you can.
So,
Yeah. Right. So you get the other one, but you're not happy.
well, maybe the statement is that, yeah, those special combinations of H left and H right have the limit. They survive the limit.
Oh yeah.
Whereas each term, like, is separately, similar to H left plus H right,
Right,
H left minus.
Right.
But
I guess we would have thought that only H left minus H right survives.
yeah, it sounds like
I mean,
we found two
I
more
think
that also survive.
these operators, right, they probably survive because they're coupling things down or whatever. If you need to.
We mean, so once you add in this P, or the size, so, yeah.
Yeah, I mean, it sounds like there's some, I don't know how to say it. Sure. Well, I guess, maybe the question is whether, yeah, I don't have it. Maybe the question is, if you just knew Sam's logic, could you apply something like this and then outcome our generators? It
Yes,
sounds close to
so,
what you're
right, I
doing.
mean, this is what we were talking about. the other day. I mean, I feel there should be, like, SYK emergence is basically generalized field theory. And
So our generators, for example, are kind of complicated.
it's a function of the fermions.
Yeah. Well,
Thought
the
they were
exact
basically
SL2 generators are very complicated. The approximate ones are somehow simple, but maybe.
Did you write down the exact ones?
No, we never. I mean, we expressed them in terms of the length, and the length is some crappy thing. I mean, we don't know how to write the length exactly, but you could, for example, compute different correlators, right, for different deltas, and then take the delta goes to 0
I
limit.
mean, what you want is something like this. Well, yeah, maybe. Right. What you want is somehow something like this where it's like integrated against the kernel or something. Log of this thing.
I'm sorry, what's that?
I don't know. Yeah.
Well, another, yeah.
There should be a way to project onto the action of this guy.
Here's the basic confusion that I have. Like, our discussion involved the Schwartzian mode and all this stuff,
Yeah.
and Sam's did it. So, what's the?
I mean, this is.
Yeah, we were having that discussion, effectively, and I'm not sure this is exactly the same as Sam's proposal. I think that's the, that's what you mean by the projection, is that? Projection in that discussion, maybe it's different. So
yeah. I mean, maybe it's related. All I meant by the projection was just, as you said, there's other crap in here.
yeah.
This isn't literally equal to this,
Yeah.
and you want to do something to
Yeah,
project onto the part of it that is.
So Sam's construction sort of, my interpretation is that it exists at infinite n. And this in principle exists at finite n and k. I mean,
Well,
but it's not
this is
declared.
well defined.
So it's well defined,
Yeah.
but of course it won't have the right answer unless you actually take the limit. So, and then there's the other question of what happens when you don't have maximum chaos, and then the proposals disagree, seemingly, because this just wouldn't work as far as I can tell. As in, your answer wouldn't give this half-sided modular inclusion, because the 2 pi would be wrong, and then it wouldn't look like that.
Right.
But Sam still has a proposal, as far as I can tell.
Right.
Yeah, that's true.
So there's some difference, and I think they agree in the
Regime where they should agree.
yeah.
But at finite
But
J.
I mean, what happens to your generators when you don't have?
Well, I think
Their generators are more similar to these because
Yeah.
these are just.
That's right. But ours also involved taking this limit. Like we took n over beta to be fixed. It could be this could be 0.
Sorry, beta.
This
You mean
could be
beta J?
Yeah, beta. So, I mean, this in particular it works when n over beta is quite large, so you could
Yeah.
consider this limit as well. But it also works for sure.
Okay.
So yeah, maybe the question is whether you can scale. Yeah, I guess we were discussing this as well. Whether you can scale temperatures with n, and still get some sort of algebra.
Yeah.
You're,
That's not obvious, right?
Or just including 1 over beta J instructions. It doesn't even need to scale with n. I think this algebraic structure is totally breaks down next to the recursive.
yes. But in particular, in this limit, for this to be, well, in this limit, I don't obviously see it Sam's construction makes sense, but our construction makes sense. Well, I'm just trying to find all the limits at which we could possibly agree or disagree.
Yeah.
Yeah, this regime, our construction still makes sense. So, I don't know. I think it'd be cool. Yeah. Whether you can scale beta, is there still an algebra with beta? It sounds like you would get not just bulk free field theory, but also this additional Schwartzian mode. If that's the algebra, you would have, in addition to the algebra of the generalized free field theory, you'd get some additional stuff, which would be relatively simple and it would correspond to the linked mode of the Schwartzian or something.
So that's not just somehow the cross product.
Yeah.
Right.
Yeah. And in particular, I mean, the correction to the entropy, so S naught you'll definitely never get, right? But the entropy has a correction that's determined, that's finite. The entropy of the black hole has a correction that goes like log n over beta J. So you might hope that you could get this in some formula. So, yeah, the S naught.
Yeah, well, that's kind of there. Oh, yeah. I see. Yeah.
I was wondering if, when people ask Vincent, like, why should we do quantum red in lab versus just like optimal protocol if you have some sort of security requirements or something like this. Right?
Yeah, yeah.
What exactly is
Isn't that related to what you said the other day?
yeah, but I think you said something more than what I would have said. Or, I mean, I think you said, I was just saying that the protocol is secure, but I think you're saying it's like optimal in some, right?
It's efficient, yeah. It's very efficient.
Yeah. But like what exactly is the task in which it's the optimal protocol?
Quantum error correction. I don't think this is saying anything more than what Hayden Pressville's just said.
Did they say that?
Well, the chaos bound is supposed to be related to optimal information. Like efficiently coding information.
I agree that it's definitely morally similar, but
Sorry,
I think you're
it's
saying
maybe not,
something more.
it's not the encoding itself is efficient, it's probably not efficient, right? It's very complicated, but it's that
It's maximally secure.
it's
I think.
maximally secure.
Yeah, I think you're saying if you want to send information in a way such that
Yeah.
the adversary can be as powerful. Well, exactly how
You're
you
just the most secure, I think.
But,
The adversary needs to have the most access to your system of any protocol.
there's no code, there's no way of sending information such that I think you're saying if the adversary is just more powerful, you just can't send the signal, and you'll fail the protocol.
Right, right. But
And what is the
if you
adversary?
wanted to hedge against the adversary being very powerful, you want to do this, right? I mean,
Like if
you want to make sure that they need to be as powerful. They need to get.
They can get any subset of the right, but they can't get more than n minus k or something. Yeah, I guess it's more of a political point.
But yeah, I mean, I agree. I think the reason the experimentalists don't care about that is because they, well, I don't know. I've just heard that they say that like quantum error correcting codes based on holography are not. They have some term for it. They're like not. Basically, the fact that they need to be k-local and all this is a pain in the ass.
But yeah, I never really understood when people said you send a classical bit of information, right? What does that mean? Of course, if you send the message on a piece of paper, the piece of paper is also a quantum system. I think what it literally means is the security requirement. That you can't, a piece of paper can be cloned, right? The information can be cloned, and so, whereas, yeah, through a bit, yeah.
Right.
In other words, I think the notion of classical information is precise only when you imagine an adversary, which can intercept the message.
Right.
In the case where you send it on a piece of paper, the adversary just wins. In the case where you send the classical bit in the teleportation protocol,
Right.
the adversary gets it, but receives no information about the qubit that you sent. I think that's what it means. I don't know. I should ask some information to it.
I guess Renato's
Or not because they're no, yeah. Of course, you can imagine formally, yeah, having classical bits in quantum systems, but if the whole world is quantum, then what does it mean? Right?
I mean,
Oh, sorry. Yeah.
Should we go to lecture?
yeah,
I kept it.
You found it?
It's correct. Yeah. Hey, no, my formulae were correct. I think I got confused. The point is that if you act with e to the IGBK, this acts on the size basis as e to the IG pk over k. But pk over k, because it's maximally scrambled, is just, or not maximally scrambled, but scrambled, is like this. So because you get this suppression by k over n, like you need g to be, you need g times k over n to be twice. So I think this is and you do need